Welcome everyone to the session about how we are using YAML for device trees. We're going to talk about a few different things on how we're doing that from a Xilinx point of view. We will see myself doing a little bit of an introduction, and then Stefano Stabellini will talk about the YAML format and how that then translates into device trees. And then at the end, Bruce we'll talk a little bit about the tool that making this transition and also do a little demo. So first, the intro. So device trees, you guys all know about device trees. It's been around for a while to describe how hardware information, the relevant hardware information for operating systems like Linux, of course, is using device trees, been doing that for a while. What has happened lately is that many RTOSes, both open source and proprietary, has been starting to use device trees. So it's becoming more and more of a standard on how to define your system, pointing out where memory is and the addresses to device registers and so on and so forth. One thing that we noticed is that device trees really only describes the system from one address space point of view, what Linux is seeing, for example. But with these heterogeneous devices that we have today, we want to be able to describe the whole system. So we've been working on system device trees for a while that builds on device trees. It's almost identical to device trees, but we are adding two things. One is on the specification side, we can actually have multiple CPU clusters. So that's the big change. There are other minor things that we are changing on the device tree side itself, but it's very minor change on the device tree, the specification part of it. But then we also have a configuration part that's for AMP systems and also for hypervisors. And the idea with that section is that we define how much of the hardware resources is going to each what we call a domain. So how much memory and which devices belongs to Linux versus belongs to RTOS and so on and so forth. So those two separate ones are the most important parts of the system device tree. And we're working with a bunch of companies and organizations that you can see on the right there to define this. So here's just a very brief introduction on how all this works. So on the left lower side, you see the device tree specification. So this is pretty much a normal device tree, but with multiple CPU clusters. So that will have all the information about how the hardware really looks like. And so you have the memory, you have devices, you have CPUs in there and so on. Right? Then in the middle, top middle there, it looks bigger, but it's actually the file is much smaller than the specification. That's where we put all these the resources, hardware resource into boxes, into different domains. And so, for example, if you have a complex system that we have here, where you have Linux running, you have Zen, the hypervisor running, and you have perhaps some RTOS, Zephyr and bare metal running, and they're divided into different segments. And as you can see, this specification or configuration becomes hierarchical, because Zen in turn includes multiple operating systems. We also have something that we're using at Xilinx that's optional, and that's something we call subsystem. So you can think of that as an outer domain that groups together things that have a similar life cycle. So for example, maybe everything on these four cores need to be started up together. And then we put that into an outer domain that we call a subsystem. And so here you can specify then exactly which memory is shared between different domains, which one is private. If you want to have protection, which we call firewalls. So very often you have these specialized configuration registers, protection registers that will protect one from another. We then have the open source tool Lopper, bottom in the middle there. And that's an open source tool that takes this information and then translates into the various different runtime clients. Zen, for example, needs device trees, Linux needs device trees, Zephyr, if you have operating systems like that, or bare metal, and also firmware. So at Xilinx, we have a plugin backend that's for our firmware in that format, because it needs to know when it's booting up things, what belongs where, and if something crashes, what do I have to restart, and so on and so forth. So this is the overall view of what we're trying to achieve here. And what we're going to talk about today is that how this description can be done in YAML as opposed to in the device tree format. Go on, next slide. So why YAML? Well, it's more intuitive than device tree. Anyone who's been dealing with device tree, it's an acquired taste, I would say, to understand. But also for tooling, when we look at IDEs and things like that, you have YAML plugins for everything. So that's the biggest reason we want to do it. And it's especially important for the domain information, the allocation, because the people who will be writing those things are people who are not that familiar with device trees necessarily. It might be a system architect that just want to move a little bit of memory from one domain to another, right? The important thing is that it's functionally equivalent to the device tree format. So it's sort of a one-to-one translation, even though we have a lot of simplifications that Stefano and Bruce will get into here. Originally, we did this for the domains part of it, but we have now extended it so we can use for all the device tree sources. And with that, I'll leave it over to Stefano to describe a little bit what we're doing with the device trees.
Thank you, Thomas. So you can really think of YAML, the YAML for device tree as two sets. The first set is to express in YAML all the same information that you have in device tree one-to-one. And this is what you see on this slide. And the second set is a series of simplifications that we make over the YAML source to make it more readable, more intuitive, and easier to understand. So let's start with the first set, which is about how to express normal device tree information, such as the nodes, properties, the hierarchy, into YAML. So the device tree nodes are represented in YAML as mapping. As mapping is a key value pair in YAML. So the key of the mapping is the node name or the node label. Node label is preferred because it's usually easier to understand. And the content of the mapping, so the value, is the content of the node. Properties similarly are also expressed as unordered key value pairs. The hierarchy is preserved in YAML by proper indentation, as you can see in this example here. So it's harder to explain than to just look at this example, and it flows very naturally. So you have device tree source on the left and YAML on the right. We have an AMBA node that becomes an AMBA key, where the value is the content of the AMBA node. This is all of these under AMBA is the value of the key value pair. The compatible string becomes also a key value pair, with compatible as a key and the strings as a value. And then we have a subnode, can0, and it becomes another key value pair where can0 is the key and the value is the content of the node again. Content of the node, which are two properties, compatible and reg, and they also get translated as key value pairs under the can0 key. As you can see, the hierarchy is the same and the content is the same. So if you have key in eyes, you'll also notice there are a few differences, such as the quotes in the strings here, that here are missing. But they are simplifications that we made and are already included here. And I'm going to go through them in a second. So as I said, why simplifications? Because the purpose of YAML is to be as easy to read as possible without losing information. So there are a few simple simplifications that we can make over YAML source that are generically applicable and make a big difference. I'm going to through all of those. They are listed here. There are just 5. And then we'll see a full example, a more complex example, and how much easier it is to read compared to device tree. So the first simplification I already mentioned is strings in YAML don't actually require quotes, so we don't use them. So an example of a compatible string in YAML is the one you see on the slide now, that has no beginning or ending quote. Maybe the most important simplification is the representation of reg. So reg is a series of 32-bit numbers, cells in the binary language, that represent multiple address ranges. And each address range is an address and a size. In order to know which 32-bit numbers represent the address, which 32-bit number represents the size, there is two additional properties called address cells and size cells that tells you how many cells is the address, how many cells is the size, and then you can finally decode all the numbers for reg. Now, if we don't do anything, also in YAML, reg will be a key value pair with as value all the number one after the other. But we can certainly make it easier to read, to write, and to understand for humans. So in YAML, we represent reg as a sequence. Well, it's a key value pair, where the value here is a sequence. So the minuses here at the beginning, each of them is an element in the sequence, and each element is an address range. But instead of just writing down numbers, we have key value pairs, a start and a size key value pair to represent the start address and the size of the range. And the numbers here, they don't need to be split into multiple 32-bit numbers. They can be 64-bit numbers and can even be human readable formats, such as 32K for gigabytes and 1G for gigabytes or megabytes or kilobytes. So the result is what you see here overall, a sequence with start and size as key value pair in each element, and a number which is a lot easier to read and understand straight away. Another related consequence of this is that we don't need address cells and size cells at all. Well, that's because we have special rules for reg. But what about other properties? So in the example here, interrupts is one of the properties for which we don't necessarily have a simplification yet. It's just a sequence of numbers. We don't exactly know which one is which. Like one of them is going to be the interrupt number, another one is going to be the mask. But still, we don't need interrupt cells to tell us how to parse each interrupt, because it can simply be a sequence in YAML, where each element is a different interrupt. Finally, p-handles. P-handles are not used in YAML, only references are used, and we can omit the AND symbol, as you can see here. So this is a reference to the interrupt controller node. Last but not least, Booleans. Booleans can have true or false as values instead of 1 and 0. Also, you should note that in YAML, we cannot have a key value pair without the value. So we cannot have ranges without a value, like we do in device tree. In device tree, under a simple bus, we typically specify ranges without a value. In YAML, it becomes ranges column true, because we need to express it as a value. And this is the full example that I hope give you straight away the right impression. So keep in mind that it's not meant for you in the audience that are probably a device tree expert. That might have been working on device tree for a decade or more, but it's meant also for people that have never seen device tree before, and they're just here to do a drive-by modification of a property or a node here or there without really fully grasping the full intricacies of the device tree specification. So under that lens, certainly for me, this looks a lot more intuitive. And if you see here, you see a sequence of address regions, and it's immediately obvious what they are. It's very easy to understand. There is a sequence of interrupts, a lot easier to understand. There are 4, and maybe we don't exactly know the numbers yet, but at least we know the individual interrupts, what they are. References without the %, and always using labels. All of it is basically summed up here. I want to, before going to Lopper, I would like to spend a couple of words on introducing further simplification. So I think we did what we could in terms of genetic simplification applicable to all. There are maybe a few more we can do, but not that many more. I think more of the further simplification are going to be binding specific. Like, for instance, it would certainly be possible to express the interrupt, each individual interrupt, as you can see on the left, actually simplify it as you can see on the right. And that depends on actually the knowledge of the specific interrupt controller binding. So in this case, I use the GigV2 ARM interrupt controller binding. Based on that, you know that the type is actually PPI, the number is hexadecimal D, level is true, trigger is low, and the mask is 0xF. And that is obviously a lot easier to read, easier to write and to understand than the one you see on the left, but it does require binding specific knowledge. So maybe an idea to explore is to introduce a formal language for bindings, individual bindings, to specify YAML simplification directly in the binding itself. And that could be an idea to scale up simplification more easily and allow each binding to have them. And with that, I'll let Bruce continue.
So we've done multiple presentations on Lopper in the past, so I'm going to go very quickly through this to get to a just a little bit of a demo. Mainly, this is here for your reference. You know, Lopper, it's been around for a while. It's a framework. It takes inputs and it produces outputs. And you know what we're going to do, what we're doing with YAML and what we're doing with the simplified device tree is not the only thing that Lopper can do. We are just using that flexibility that's always been built into Lopper to actually extend and do this processing. So it's any number of things that we can do with Lopper in this example. So and what we'll see here is some Python assists. We'll see some what are called LOP files, which are sort of base commands, as well as a front end and a back end. So we can jump to the next slide. And so, yeah, this is the point is that, you know, we're trying to create this as a common source for different tools to manipulate device trees. And as I mentioned, there's sort of core tree manipulation routines inside of Lopper, but it can read DTS, ETB, YAML, inputs and outputs. It uses different parsers, and we can do different types of front ends and back ends and analysis engines to do modifications to the tree. This is, and what we're going to run here, it's sort of this configuration where, in particular, we're talking about we can do multiple inputs in one run. We're talking about reading in YAML, which goes through the standard sort of Python YAML processing libraries to create a dictionary structure, which then goes through an importer, which creates this sort of internal representation of a tree. Which we then run translation routines and domains and assists and LOP files operations against it. And that modifies just the internal format, just the tree, which then goes to an exporter back to a dictionary format, which these various backends understand. And then we can write out any number, any of the inputs. So we can go from any input to any other output and vice versa. They're not completely one-to-one, but the flexibility is there to do that sort of transformation. And with that, I will jump to a very quick demo. I have one that is showing how we can expand the domain processing that Thomas talked about, and a second one that shows a simplified device tree being expanded that Stefano was talking about. So I will share my terminal here. And so the very first one is I was mentioning is it is a firewall. It's a firewall reference. So it is a set of domains and resource groups and subsystems that are specified. And the part that we're actually most interested here is firewall conf, which specifies a domain and a keyword. And there's multiple different ways to specify this protection information. But that needs to be translated into device tree and into different formats that either boot or other tools can understand. So we do a Lopper run. It's telling it to do Lopper. It's telling it to do this X YAML says do YAML expansion. The input is that firewall ref. And what comes out is in this case, we're writing out a DTS. and of course the paste doesn't want to work. And so what we ended up with is now a device tree representation of those domains and subsystems. And in particular, the firewall conf has been expanded into p handles and flags and the proper format. And even it has determined that there needs to be a default as well as a specific firewall conf, and it's generated all that information. So, that's one use with a specific set of operations being run against it. The second one is against the simplified device tree format that was just on the slide. So, we have compatible, we have CPUs, we have the interrupt, we have timers, but showing how we can use the tooling to bring to generate a device tree and sort of fill in those blanks. So I'm basically running the same command line. I've specified a few extra things just to tell Lopper what to do with YAML in particular, because there's certain different ways we can interpret it. And you can see as this run, it expanded the reg nodes for AMBA. It located and created p handles for nodes that had certain properties that it knew to look for. Well, Lopper didn't know to look for, but the input YAML expansion knew to look for. And then it generates some CPU cells and different things. So when we now look at what was that same YAML, it's not going to cut and paste, of course, that Stefano showed in the slides. So now we have CPUs, which have a compatible, we have address cells, size cells, mask cells that are generated. We have clocks that have been expanded, and all the information is in the proper structure. And in particular, you can see here that I just went over with the highlighting, the sequence of reg was expanded, and the interrupt parent was created into a reference, a symbolic reference to the interrupt controller. So it has gone through, and even if you want to see here, the range's true Boolean has been converted into the proper device tree. So there was multiple levels there. There was sort of core YAML translations that it knows how to do the basic types, and then we ran commands against it to do extended processing and sort of add data, add information, realign nodes, move things around, and that's sort of a second part of the processing. And that is it. And this is all available in the link on the GitHub on the devicetree.org Lopper repository that was in my slides.